HAR feature detection, like any other form of computer vision processes, is highly susceptible to noise and error. The tracker, however, requires a much more accurate estimate of the face position. There are several noise removal filters that exist. Of these, a Kalman filter was chosen because it is the most widely used and the most reliable method for predicting the state of a noise-susceptible system. The Kalman filter is widely used in all aspects of technology, from missile guidance to temperature measurements and any system where noise is an important factor. The underlying concept of Kalman filters is a discrete-time linear dynamic system. This system, simplified to its most basic form, depends upon two equations. The first of these models how the system changes with each time step. X of k refers to the state of the system at the time step k. The state of the system is simply a matrix of values containing quantities that define how the system behaves. In conforming with standard Newtonian models of motion, the only three quantities used to describe a moving object are its position, velocity, and acceleration. X of k minus 1 is the state of the system in the same form as X of k, but representative of the system at the previous time step. Because what is defined as the state varies from problem to problem, linear dynamic systems use a matrix, here shown as A, to describe the operation used on the previous state to calculate the current state. Because we assume constant acceleration, this operation is fairly simple and uses standard physics kinematic equations. This lets us define A as the following, and when multiplied by X of k minus 1, gives us X of k. The second equation deals with how the measured value of a system, represented here as Z of k, relates to the X of k that is used in prediction calculated by the first equation. In a noiseless system, Z of k and X of k are equal, and B is an identity matrix. However, real-life systems always contain noise factors, here represented by W of k and V of k. Both of these noise factors are modeled as Gaussian noise functions. This assumes that the measured noise is evenly distributed around the truth value, with a certain range being considered good accuracy. The Kalman filter is an algorithm layered upon a linear dynamic system. It consists of two distinct phases. The predict method uses the previous time step state to predict the current time step state, taking into account noise. The other method, update, takes measured values and updates the current state estimate by modifying the predicted state values. Because both of these are two separate processes, the Kalman filter can predict the motion of an object even when no measured input was given, ensuring a continuous stream of tracking data.